Hello, my name is Svenn Ove Hoem, and I am a former mechanical engineer student at NTNU, Norway. Thanks for having me at this conference. I'm going to present my master thesis, Optimizing a Gas Diffusion Layer with Mathematical Defined Structures. I wrote this thesis with my supervisors Jan Torgersen and Robert Bock. This is Norway, and here is NTNU Trondheim. Norway has an extensive coastline and tremendous potential for more renewable energy, especially in the north where it is constantly windy. But how to export this electrical energy? Power lines are not feasible to transport energy to the south or even further to the continent. Hydrogen is a very good solution for transporting this renewable energy to wherever in the world it is needed and coincidentally also serve as energy storage, short-term and long-term. Norway has quite a bit of professional experience with water electrolysis, driven by Norsk Hydro, who later switched over to gas reforming to obtain the hydrogen they needed. Now there are companies emerging that produce green hydrogen in Norway. With a large untapped potential to renewable energy production, Norway could become the source of green hydrogen for the European market. What to do with all the hydrogen? We need fuel cells. Fuel cells. The fuel cell is built up by the bipolar plates, the gas diffusion layer, catalyst layer, and electrolyte. On the upper left here, we have the bipolar plate with machine flow channels. The bipolar plate needs to homogeneous distribute reactants over the whole surface area of the fuel cell and efficiently remove reaction product water. Here we can see the membrane electrode assembly, and here is the catalyst layer, which need high catalytic activity and high amount of reactant sites. Here is the gas diffusion layer, which is the layer of focus in my master thesis. The gas diffusion layer is used to establish the chemical gradient to diffuse reactants to the catalyst layer and remove produced water. It also needs low ohmic resistance for electron flow. Ohmic and mass transport tuning. In my master thesis, I investigated the gain in conductivity and permeability by optimization of microstructural morphology. On the lower left, we have traditional gas diffusion layer made of carbon paper. And the upper left, we have a cubic lattice gas diffusion layer, which is order structured. By using these order structures, we may enhance electron conduction between the bipolar plates and catalyst layer, promote reactant and product transport to and from the catalyst layer, heat transfer, and mechanical support to the membrane. On the graph to the right, we can see a traditional gas diffusion layer and a cubic lattice gas diffusion layer, and we can see the conductivity gain and permeability gain is notable. The candidates. For optimization of the microstructural morphology, we have 4 candidates. To the left, Schuangerid. Next one is Schwarz-P beam, and cubic lattice. The first 3 are fully mathematical defined structures and can be found natural in nature. Dimension structures can be divided into a solid and a void. In the solid, there are electron transport, and in the void, there are mass transport, such as reactants and produced water. Here is a cubic lattice, Schwarzschild beam, Schwinn-Gyrrid, Schwarzschild. Schwinn-Gyrrid and Schwarzschild has a much higher surface area than the cubic lattice and the Schwarzschild beam. In addition, Schwinn-Gyrrid has 2 voids and 1 solid, same with the Schwarzschild beam. The chosen software to calculate the electrical conductivity and the permeability is ANSYS. But first we needed to generate the structures. The software and topology is specialized in generating mathematical defined structures. So the picture to the left shows a Schwarzschild structure, which is meshed and exported as step to ANSYS, where it is cleaned and patterned to the desired size. The structure is then meshed in the ANSYS meshing module, and a sensitivity analysis is performed on the mesh to ensure the quality. The boundary conditions in the ANSYS electric module is a current inlet of 3900 milliamps and an electron outlet of 0 volts. We then utilize Ohm's second law and calculate the voltage potential between the inlet and outlet and obtain the effective conductivity and calculating the conductivity ratio. Conductivity. Here we can see the effective electrical conductivity, and here is the porosity. We can see that Schwarzschild and Schwinn-Gyrrid has the highest effective electrical conductivity, followed by cubic lattice and Schwarzschild beam. If we compare them to results in literature from Liblet and Becker on traditional gas diffusion layers, we can see that all the structure performs superior over the true plane direction of the gas diffusion layer, and cubic lattice and Schwarzschild beam have very similar performance to the in-plane direction of gas diffusion layer. The results shown in the former graph are plotted in this slide. For the cubic lattice, we can see that the current density are pretty uniform along the beams in vertical directions. The Schwarzschild beam, the current densities are much greater in this section where the cross-sectional area is low. The Schwarzschild has pretty uniform cross-sectional area through the whole structures and have no hotspots of current densities. The same goes for the Schwinn-Gyrrid. One of the most important factors to understand when we talk about electrical conductivity is the tortuosity, which is the length which the electron travels through the structures divided by the length of the bounding box. Here we can see the Schwarzschild structures, which are plotted with the vectors describing the current densities. We can see that when the vectors are changing directions, there are induced tortuosity, which increases the length the electrons has to travel through the structure, and hence increasing the resistance. Here we can see the tortuosity for the different structures. Cubic lattice has almost no tortuosity, followed by the Schwarzschild, which is the best performing structures, then Schwinn-Gyrrid and Schwarzschild beam, which is the least performing structure. The main takeaways are that low variation in cross-sectional area gives high utilization of the volume and low resistance of electron flow. Structures with zero mean curvatures are found to be the best performing. Also, low tortuosity gives high conductivity. Next, we are going to talk about permeability. We are using ANSYS Fluent to do all the permeability calculations. In the Fluent module, we are setting the inlet to 0.01 Pascal and the outlet to 0 Pascal. The external boundaries and internal boundaries are no-slip walls. ANSYS uses the Stokes equation, steady state, for incompressible fluids. There is one phase, water, and we are assuming a very low Reynolds number. Then we are calculating the permeability coefficient with Darcy's law. First picture here, we can see the velocity plot for the cubic lattice. We can see that there are a main stream through the cubic lattice that is not obstructed by other than the horizontal beams. Same with the Schwarzschild beam, but there is even less obstructions from the horizontal members. The story is different for the Schwinn-Geroid. The flow channels in the Schwinn-Geroid are helicoiled and makes the stream rotate through the structure, which is a really tortuous path. And for the Schwarzschild, there are really narrow sections of the flow which restricts the flow. A big takeaway here is that the Schwinn-Geroid and Schwarzschild has really high surface area, which induces very much energy loss at the surfaces. Here are the results from the permeability analysis. We can see the Schwarzschild beam has the highest permeability, followed by the cubic lattice and Schwarzschild and Schwinn-Geroid. Permeability, hydraulic diameter. Okay, for the cubic lattice, the inscribed diameter is very large compared to the unit cell. But for the Schwinn-Geroid, we can see that the flow channel is fairly large, but when we look at the flow channel from above, the inscribed diameter is really low because the flow channel is alternating. Here we can see the permeability compared to traditional gas diffusion layers. The Schwarz beam and cubic lattice are high performing, and you can see that they perform better than most other structures except the in-plane direction of Becker. The Schwarzschild and Schwinn-Geroid performs bad compared to the rest. The main takeaways from the permeability is that the optimal structure needs to have a low surface area. That's the most important thing. Largest possible inscribed diameter, low tortuosity, and circular shape of the inlet to the unit cell. Here is a selection chart that we made from all the structures. Here we have the effective conductivity ratio, effective water permeability, and porosity. The dotted lines are the effective conductivity, and the solid lines are the effective water permeability. So here is the intersection between effective water permeability and effective conductivity for a traditional gas diffusion layer. The Schwarzschild beam is here, cubic lattice, which is the best performing, and Schwinn-Geroid and Schwarzschild beam. thank you to the participants in this project.